The principles of value management. Value management, VM, is a structured approach to defining what value means for a given project or process and how it can be maximized. It ensures that all stakeholders have a common understanding of value and work collaboratively to achieve the best possible outcome. Key principles. 1. Functionality. VM focuses on understanding the functions that need to be delivered, rather than the means of delivery. This approach encourages innovative thinking and helps avoid unnecessary constraints. 2. Multidisciplinary teams. Successful VM relies on the collaboration of a diverse group of people with different expertise and perspectives. This diversity ensures a comprehensive understanding of the project or process and promotes creative problem-solving. 3. Stakeholder involvement. Engaging all stakeholders early and continuously in the VM process is crucial. It ensures that their needs and expectations are understood and met, leading to higher satisfaction and better outcomes. 4. Clear objectives. VM requires setting clear, measurable, unambiguous, and ambitious targets. These objectives should align with the organization's values and goals and be communicated effectively to all team members. 5. Methodology. VM employs a systematic methodology, which includes the following steps. Preparation. Define the scope, objectives, and criteria for success. Information. Gather relevant data and insights from stakeholders and other sources. Function analysis. Analyze the required functions and identify potential improvements. Creative phase. Generate ideas to enhance value by improving functions or reducing costs. Evaluation. Assess the feasibility and impact of the proposed ideas. Development. Develop the selected ideas into detailed action plans. Implementation. Execute the action plans and monitor progress. Review. Evaluate the outcomes and document lessons learned for future projects. 6. Continuous improvement. VM is an ongoing process. It should be integrated into the organization's culture and applied to all projects and processes. Continuous review and improvement ensure that value is consistently maximized. Application. VM can be applied at any stage of a project or process, from initial concept through to delivery and operation. It is particularly beneficial during the early stages when the potential for influencing value is highest. By adhering to these principles, organizations can achieve significant improvements in performance, cost-effectiveness, and stakeholder satisfaction. The application of value management. Value management VM can be applied at various stages of a project or within an organization to maximize value and ensure alignment with objectives. Its application involves several key activities. 1. Strategic planning. VM is used during the strategic planning phase to ensure that the objectives and goals of the organization are clearly defined and aligned with the overall mission and vision. This helps in setting a strong foundation for subsequent activities. 2. Project initiation. At the project initiation stage, VM helps in defining the scope, objectives, and success criteria. It ensures that all stakeholders have a shared understanding of the project's purpose and expected outcomes. Design and development. During the design and development phase, VM techniques are used to analyze the functions of the project and explore various alternatives to achieve the best value. This includes function analysis, cost-benefit analysis, and creativity techniques to generate innovative solutions. 4. Implementation. VM continues to be applied during the implementation phase to monitor progress, ensure that the project stays aligned with the defined objectives, and make necessary adjustments. It involves continuous evaluation and feedback to improve processes and outcomes. 5. Operation and maintenance. In the operation and maintenance phase, VM ensures that the project delivers ongoing value and meets the user's needs. It involves regular reviews and assessments to identify opportunities for improvement and cost savings. 6. Review and feedback. After project completion, VM involves a thorough review to assess the project's success and learn from the experience. Feedback is gathered from stakeholders to identify best practices and areas for improvement, which are then incorporated into future projects. Benefits of applying value management. Improved decision-making. VM provides a structured approach to decision-making, ensuring that all options are considered and the best possible solution is chosen. Enhance stakeholder engagement. By involving stakeholders throughout the process, VM ensures their needs and expectations are met, leading to higher satisfaction and support. Cost savings. VM helps in identifying cost-effective solutions and eliminating unnecessary expenditures, resulting in significant cost savings. Increased innovation. VM encourages creative thinking and the exploration of alternative solutions, leading to innovative outcomes that deliver greater value. Better risk management. VM helps in identifying and mitigating risks early in the project, reducing the likelihood of issues arising later. Implementation framework. Preparation. Define the scope, objectives, and criteria for success. Gather relevant data and insights from stakeholders and other sources. Function analysis. Analyze the required functions and identify potential improvements. Creative phase. Generate ideas to enhance value by improving functions or reducing costs. Evaluation. Assess the feasibility and impact of the proposed idea's development. Develop the selected ideas into detailed action plans. Implementation. Execute the action plans and monitor progress. Review. Evaluate the outcomes and document lessons learned for future projects. By following this framework, organizations can ensure the successful application of VM and achieve significant improvements in performance, cost-effectiveness, and stakeholder satisfaction. Value management, VM, in process industries focuses on optimizing processes, enhancing efficiency, and achieving cost-effectiveness while ensuring safety and compliance with regulations. Here's a detailed breakdown of how VM principles and methods are specifically applied in process industries. Specifics of value management in process industries. 1. Function analysis. Purpose. Identifying and understanding the essential functions of a process or system is critical. This involves breaking down processes into their fundamental functions to assess their necessity and performance. Application. In the process industry, function analysis might focus on operations such as refining, chemical reactions, material handling, or energy consumption. The goal is to identify areas where improvements can be made without compromising quality or safety. Example. In a refinery, function analysis can help in identifying critical control points in the distillation process, optimizing heat exchangers' efficiency, and ensuring that each unit operation contributes effectively to the overall process. 2. Value engineering. Purpose. This involves assessing the cost-to-function ratio to ensure the most cost-effective solutions are implemented without sacrificing performance or safety. Application. Value engineering in process industries often involves evaluating equipment and material choices, process routes, and technology options to find the best value solutions. Example, when designing a new chemical plant, value engineering can be used to compare different types of reactors, materials of construction for pipelines, or control systems to ensure that the chosen options provide the best value for the investment. 3. Design to cost. Purpose. Setting cost constraints for process designs and ensuring that the project stays within budget while meeting all functional requirements. Application. This approach requires rigorous cost estimation, budgeting, and cost control measures throughout the project lifecycle. Example. In designing a new process line for food production, cost constraints might be set for each phase of the project, from initial design through to commissioning. Cost estimation tools and techniques are used to ensure the project adheres to the budget while also meeting all regulatory and performance standards. 4. Design to objectives. This approach not only considers financial constraints but also incorporates other critical objectives such as sustainability, safety, and regulatory compliance. Application. In process industries, this means designing processes that minimize environmental impact, maximize safety, and comply with industry regulations. Example. A pharmaceutical manufacturing facility might use design to objectives to ensure that the process design not only meets cost targets but also achieves high standards of cleanliness, product purity, and regulatory compliance with bodies such as the FDA or EMA. 5. Stakeholder involvement. Purpose. Engaging all stakeholders, including engineers, operators, safety experts, and management, to ensure that their needs and expectations are considered. Application. Regular meetings, workshops, and feedback sessions help gather insights and ensure all perspectives are included in the decision-making process. Example: during the design of a new petrochemical plant involving stakeholders from different departments, engineering, operations, maintenance, safety, and environmental compliance, helps create a design that is well-rounded and addresses all critical aspects of the plant's operation. 6. Continuous improvement. Purpose: implementing a culture of continuous improvement to regularly review and enhance processes. Application: using tools such as Six Sigma, Lean Manufacturing, and Kaizen to identify inefficiencies and implement improvements. Example: a continuous improvement program in a manufacturing plant might focus on reducing energy consumption, minimizing waste, and improving throughput by regularly reviewing and optimizing process parameters. Benefits of value management in process industries. Enhanced efficiency. Streamlined processes and optimized resource use lead to higher efficiency and productivity. Cost savings. Identification and elimination of unnecessary costs help maintain budgets and improve profitability. Improved safety and compliance. Ensuring that all functional and regulatory requirements are met reduces the risk of accidents and legal issues. Innovation and creativity. Encouraging innovative solutions and alternative approaches leads to better overall process performance. Stakeholder satisfaction. Meeting the needs and expectations of all stakeholders results in a more cohesive and motivated team, leading to better project outcomes. By applying these VM principles and methods, process industries can achieve significant improvements in performance, cost effectiveness, and stakeholder satisfaction. In the context of value management, VM, in process industries, several specific tools are commonly used to enhance efficiency, cost effectiveness, and overall value. These tools help in the systematic analysis and optimization of processes, equipment, and resource utilization. Here are some of the key tools. Specific tools for value management in process industries. 1. Function Analysis System Technique, FAST. Purpose: helps in identifying and understanding the functions of a process or system. Application: used to break down complex processes into their basic functions and understand the relationship between them. Example: in a chemical plant, FAST can be used to analyze the functions of a distillation column, identifying areas where improvements can be made. 2. Cost-benefit analysis, CBA. Purpose: evaluates the costs and benefits of different options to determine the best value solution. Application: used to compare various design or process alternatives based on their economic impact. Example: comparing the costs and benefits of using different materials for pipelines in a refinery to determine the most cost-effective option. 3. Life Cycle Cost Analysis, LCCA. Purpose: assesses the total cost of ownership of a process or equipment over its entire life cycle. Application: helps in making informed decisions about investments by considering initial costs, operation, maintenance, and disposal costs. Example: evaluating the life cycle costs of different types of compressors in a gas processing plant to select the most economical option. 4. Value Stream Mapping, VSM. Purpose: visualizes the flow of materials and information through the process to identify waste and opportunities for improvement. Application: used to map out the current state and design a future state for the process with reduced waste and improved efficiency. Example: creating a value stream map for the production line in a pharmaceutical plant to identify bottlenecks and streamline the process. 5. Benchmarking. Purpose: compares the process performance against industry standards or best practices to identify areas for improvement. Application: used to set performance targets and identify best practices that can be adopted. Example: benchmarking energy consumption in a petrochemical plant against industry standards to identify opportunities for energy savings. 6. Root Cause Analysis, RCA. Purpose: identifies the root causes of problems or inefficiencies in the process. Application: helps in diagnosing issues and implementing corrective actions to prevent recurrence. Example: using RCA to determine the causes of frequent equipment failures in a food processing plant and implementing solutions to improve reliability. 7. Failure mode and effects analysis, FMEA. Purpose: identifies potential failure modes and their effects on the process to prioritize and mitigate risks. Application: used to systematically evaluate the risks associated with different components or processes. Example: conducting FMEA for a new production line in a manufacturing plant to identify and address potential risks before commissioning. 8. Total cost of ownership, TC. Purpose: assesses the comprehensive cost of acquiring, operating, and maintaining an asset over its entire lifespan. Application: used to compare the long-term financial impact of different investment options. Example: comparing the TCO of different types of heat exchangers in a chemical processing plant to select the most cost-effective option. Design of experiments. Purpose: plans and conducts experiments systematically to understand the effects of various factors on process outcomes. Application: helps in optimizing processes by identifying the critical factors and their interactions. Example: using DOE to optimize reaction conditions in a chemical process to maximize yield and minimize waste. 10. Pareto analysis. Purpose: identifies the most significant factors contributing to a problem or inefficiency. Application: used to prioritize issues based on their impact to focus improvement efforts on the most critical areas. Example: applying Pareto analysis to maintenance data in a refinery to identify the most common causes of equipment downtime. By utilizing these specific tools, process industries can systematically analyze their processes, identify opportunities for improvement, and implement solutions that maximize value, enhance efficiency, and ensure cost effectiveness.